Swayam Prabha. Digital India. Educated India.
Welcome to the class on transport phenomena. I just heard someone tell me if it's transport phenomena, he won't do it. He will do it only if it is advanced transport phenomena. So it is advanced transport phenomena, but I call it transport phenomena so that people don't get intimidated or scared. Okay. So what I'll do is in this first class, which is aimed at all the master's students and the PhD students, is by way of introduction today. Just try to tell you something about the history of how it started and what kind of a role transport phenomena plays in chemical engineering. Okay, and from tomorrow we will get started on the details of the course. So before we get started on the technical aspects, what I like to do is we will basically be following two books. I mean, one is the classical book of Bird, Stewart, and Lightfoot. I mean, people call it BSL. Okay, you may have used this in your undergraduate class. Okay, the second thing that we will look at is advanced transport phenomena. By Gary Leal. Okay, the name of this book is Transport Phenomena, the first book. So these are the books which we will be using, okay, by way of reference books and stuff like that. We will make sure you have access to these books, either hard copy or soft copy. And the next thing that we will do is the grading pattern. Which is going to be almost the same as what you saw last semester for the math course. Quiz 1 will be 15%. Quiz 2 will be 20%. Assignments will be 40%. And the final exam will be 25%. At this point of time, I have not decided whether to have any credit for attendance, but I might change my mind and I might do that. Okay. So that's basically taking care of the administrative aspects of this course. The books which you will be using, okay, which we will be following, and how you're going to be evaluated. Okay. So now that that is done, you know, when before chemical engineering came to be in the form that we see it today, the curriculum that you are seeing, the courses that you are going through, the chemical process industry existed. Okay, there were industries which manufactured fertilizers. There were industries which did petroleum refining, and you can think of there were cement industries, and the initial thought process was that each industry has its own unique um, characteristics, has its own unique processes, okay, and so a person who was basically trained in operating an ammonia plant could not necessarily operate a cement plant, or vice versa, okay, because the thing was, you know, oil technology is different, fertilizer technology is different, rubber technology is different. And so everybody was thinking, I mean, you need to have specialization. In fact, not too long ago, you would have a lot of courses. Even now, some institutes have specialization courses, undergrad, in oil technology, in plastic technology, whatever. But then it turns out that we had this inspector whose job was to inspect the running of all these plants, and he would go from one plant to another and try to understand how things are functioning. And then he realized that although it appeared that all these plants were completely different, okay, there was a lot of commonalities, a lot of same basic principles which basically, you know, uh, are underlying for each operation, okay. So that's when they started looking at the curriculum in this form, rather than talk about specialization for a specific field. You talk in terms of understanding the underlying principles, because if you understand the underlying principles, you should be in a position to apply it to any industry, okay. So there was a radical change in the thinking of the process. Otherwise, if you are trained in fertilizer technology, you won't be able to work in any other industry, because you only know how to do fertilizer, and you don't realize that there is a similarity between the processes that are happening in fertilizer industry with what is happening in some other industry, okay. So at the end of the day, there was a realization that all these industries are basically based on some basic unit operations, and the thrust was on understanding these unit operations. And when you get a degree in chemical engineering, the focus is on understanding these individual processes, which gives you the flexibility to work in any environment, okay. So that's the whole idea. So that's how the philosophy changed, and today the kind of courses that you are doing, in your undergraduate curriculum, in the postgraduate curriculum, is basically harping on the fundamentals, okay, which basically gives you this versatility to work across the discipline. So that's how transport phenomena came out to be in the shape what it is right now. And so when you talk about transport phenomena, okay, the thing which comes to mind you have three things in mind. One is fluid mechanics, then you have heat transfer, and finally mass transfer, okay. So I mean, you have seen these subjects, okay, these topics in your curriculum in some form, but what is important is that there is a unifying thread in all these three, okay. which is what we want to emphasize, which is what we want you to understand and appreciate, so that you will have the confidence to apply the basic fundamentals to any situation, any process, any system. Okay. So, in fact, if you talk about a chemical reactor, you will have, if it's a packed bed reactor, you will have flow. Therefore, you have fluid mechanics. So, you have flow through the porous media. Then this reactor can be, of course, sustaining a reaction, because of which the reactant has to go into the catalyst. So, there is mass transfer involved, and this reaction could be exothermic or endothermic, and therefore, there is going to be heat transfer, heat effects, energy effects. So, when you look at any particular system, it would look like systems will basically have all the three inbuilt in it. Okay, fluid mechanics, heat transfer, and mass transfer. So, there can be systems of that kind. So, systems, let's say a packed bed reactor has reactions, mass transfer, okay, heat transfer, and fluid mechanics. Now, what you've done in the past is possibly looked at only one specific aspect of the problem of the system. For example, if you're doing a course in fluid mechanics, you would look at only what is the pressure drop across a packed bed. You will say it's given by Darcy's law. If you're doing a course in heat transfer, then you look at the energy effects. Okay, or if you have a packed bed reactor, you may assume that the flow is uniform and only concentrate on the species transport. So, you basically break down this very complicated problem where you have everything happening: species transport, mass transfer, heat transfer, fluid mechanics, momentum transfer. Okay, and then you look at a small aspect. That's what you've been doing. But there will be times when you have to look at the entire system. Okay, where you have to look at all mass balance, energy balance, and momentum balance to understand the system better. The other important thing is there is a lot of similarity between heat transfer, mass transfer, and momentum transfer. And if you understand one of these things properly, it is easier to understand the other subjects. Okay, so because things are similar. So, for example, in heat transfer, in a solid, there is going to be conduction, and in the equivalent of that in mass transfer will be diffusion. Okay, and if you remember the law of conduction, Fourier's law of conduction is heat flux is proportional to the gradient of temperature. Similarly, the mass flux is going to be proportional to the gradient of concentration. So, there is an analogy between all these different subjects. Okay, and therefore, what we are trying to do in this course is trying to develop this overall perspective across these three disciplines of fluid flow, mass transfer, and heat transfer. Okay, so rather than focus on one aspect of a system, we want to understand system behavior fundamentally. Okay? So our focus is on getting a fundamental understanding, and we want to exploit the similarities in heat transfer, mass transfer, and momentum transfer or fluid mechanics. Okay? What do I mean by that? I mean, for example, in heat transfer you have Q, the flux is minus K, the gradient of T. This is Fourier's law. And then in mass transfer, K is minus D, gradient of C. This is Fick's law. And this is something which you have come across before. The important point is that we are assuming here, for example, there is no convection, no flow. Okay, there is only conduction or diffusion taking place. Now, why is it important to have this kind of a fundamental understanding? Otherwise, I mean, when you are in an actual system, you take a reactor, okay, or a heat exchanger, any unit you take, any system you take, there are a lot of details in the system, right? I mean, you need to know where the inlet is, how is the inlet coming into the thing, is there a gas sparger, what is the design of the sparger. So, that is one level of detail at which you need to understand the design of the reactor to be able to predict the performance. Okay. So, one thing is in large scale system, we need to include the specific geometry, inlet and outlet conditions and all the details. I mean, if you want to understand how a reactor is behaving, you will say, look, I need to understand what is the size of my packing, is it uniform particle size, is it uniform catalyst pellets, all that detail, where does that fit in, okay? And then the problem gets too complicated. So, here we have a very complex system, okay? And so what you do is you will carry out a lot of experiments, generate a lot of data, and then use something like an empirical approach. Okay? So here we will try to improve our understanding using an empirical approach. So you start making some correlations and you try to say this is how I believe the system works. That is limited to whatever the particular system is. Tomorrow, if you want to make some modifications, say if your plant is running at a particular efficiency and you want to improve it, okay, how do you go about making changes? Because you really have not understood the fundamental things happening in the system, okay. So, if you want to think in terms of making the system perform better, how would you go about doing it? You really wouldn't know. You would possibly do it by trial and error. Okay. To give you a very specific example, if you are trying to do an extraction, let us say of some pollutant from water into some organic phase, okay, how good the extraction is will depend upon things like the flow. It will depend upon the liquid you are using to extract. Okay. So, but what are the exact properties which are going to determine the process? I mean, you know, qualitatively, if I use benzene for extraction, I have 20% efficiency. But what about using toluene for extraction? Will it give me better? And what decides it? I mean, one way is for me to do the experiment. The other way is to understand what is the basic difference between benzene and toluene, which is making my system perform better. Okay. So, that is the whole point. What is it that is fundamentally different? Is it solubility of your pollutant? Is it something else? So, this kind of an improved understanding, okay, is what we are focusing on, so that you can better design systems, better design unit operations. Okay. So, the whole emphasis, we are not going to be sitting here and doing one way of analyzing the system is by analyzing the full system with all the details. And there is one school of thought, one approach, computational fluid dynamics, which does that. Okay. They will write all these equations, the mass balance, all these equations will be written, and all of this will be solved. And today there are lots of packages, ANSYS is there, COMSOL is there, which do that. But it is important for you to understand the fundamental aspects, so that you can use these packages efficiently, because these packages will always give you some result. And whether this result is correct or not correct, that ability you should have. Because you go to the computer, you feed in some parameters, the software package will give you some result. Okay. Now, you have to make sense out of the result, interpret it. You have to make sure that you have used the package properly. Okay. And in order to make sure that you use the package properly, you need this course, transport phenomena, which tells you the fundamentals, so that you can think and interpret the results. Okay. So, we are not going to be using packages in this course at all. We are not going to be teaching that. What we are going to do is look at the fundamental aspects, which will help you interpret your results and the behavior of systems. That is the focus as far as the course is concerned. Okay. So, our course is basically focused on understanding fundamentals, and so let us come to some specific things. What are the interesting, challenging problems that we have? The transition from laminar to turbulent flows. I mean, most of you know that this happens at a Reynolds number of 2100. Okay. I mean, this has been studied experimentally by Reynolds. He did his famous experiment in a pipe, and he found you have a laminar profile for low Reynolds number, for high Reynolds numbers you have turbulent. So, how does this change occur? Only thing you are doing is changing the flow rate. Okay, changing the velocity. You have a fixed system, you keep increasing the velocity, the average velocity, you have a change in the behavior. So, this is one question which you want to try and understand fundamentally, because you may be interested in having a system which runs at laminar flow, but at higher Reynolds numbers. So, the question is, can I have laminar flow at high Reynolds numbers, higher than 2100? Okay. So, because in your particular application, Reynolds laminar flow is important, but your flow rate is very high. So, the question is, can we delay the onset of turbulence. Can we have laminar flow for Reynolds number, let us say 10 power 4 or 10 power 5? And the answer is yes. So if you were to, there are people who have shown that you can have laminar flow for Reynolds number as high as 10 power 5. Okay? The answer is yes, it is possible. So, I mean, then you need to understand how you can possibly understand, how you can possibly generate laminar flow, okay, at high Reynolds number. This is kind of not what you know in your undergraduate class. You know more than 2100 is turbulent. But there could be situations where you do your experiments carefully, you make sure that there are no disturbances in the system, and you can possibly get laminar flow at a very high Reynolds number. Okay. Talking about Reynolds number and turbulence, so this is for single phase flow, but there can be many examples where you may have two phase flows. Okay, you may have oil and water, you may have gas and water, so you can have more than one phase flowing in a particular pipe. Okay, so supposing I want to extend this idea to a two phase flow, let us say of oil and water. So the way the two liquids will flow in a pipe, there can be different kinds of flow regimes, flow patterns. Okay, so different flow regimes are possible here. For example, the extension of the laminar flow. So, in the single phase flow, we had laminar. So, what will be the analog of laminar flow here? Supposing you have flow between parallel plates, okay, this is a plate and this is a plate here. If it is single phase, this is for the single phase. Okay, that is your laminar flow profile, provided your Reynolds number is sufficiently low. But what about the two phase? You may have oil and water. Can we have the two liquids flow side by side? Okay, so this is what we call stratified flow. So you have zero velocity here, something like this, okay. So this is one possible way by which the two liquids are going to flow side by side. Okay, one possible way the two liquids will flow, and this is the extension of this thing, the laminar flow of the single phase problem. Now, is it possible to have other flow patterns? I may have oil, this could be oil drops, and this could be water. Water is my continuous phase and oil drops are present. Or can I have the other way? Can I have water drops and oil? So the continuous phase is oil here, and here water is the continuous phase. What do I mean by continuous phase? You have a continuous phase in which the drops of the other phase are there. The other phase is a dispersed phase. Okay. So to keep life simple, I just have two phases, and the drops. This is the dispersed phase. The question is, under what conditions will you get a flow like this? Under what conditions will you get a flow like that? What decides this? Okay, because if you understand it, then you can design your reactor, your experimental setup for a particular flow regime, and then you can possibly get better efficiency. For example, you know what is hydrophobic, hydrophilic. Hydrophilic means something likes water. So if I were to coat this surface and make it hydrophilic, then water will have it likes water. So water will be the continuous phase. If I make it hydrophobic, the surface does not like water, oil will be the continuous phase. So I need to understand these concepts of hydrophobicity and hydrophilicity. Okay, depending on whether I want this or that. So this could be for, as an example, this will be for a hydrophilic surface. And this is for a hydrophobic surface, when oil will be the continuous phase. The surface does not like water. Okay. The other thing which is important is the surface tension. When you talked about single phase flows, you were only interested in viscous effects, viscous forces and inertial forces. But when you have two phases, there is an interface, and there is going to be a surface tension associated with it, an interfacial tension associated with it. Okay. So depending upon, now there is one more force which comes in, okay, the interfacial forces, and depending on the magnitude of the interfacial forces, if the interfacial forces are high, I'll get this kind of a droplet flow. So this flow pattern that I have drawn is a droplet flow pattern. Okay, so this is so that was stratified flow. This is droplet flow. So, and this is decided by an extra force which comes in, which is surface tension. Okay, so the Reynolds number, you know, ratio of inertial to viscous, but now surface tension force also has to come, and then I will have a number like a capillary number or a Weber number, where I talk about ratios of viscous forces to inertial forces, viscous forces to inertial forces to interfacial forces. Okay, so that is what is going to decide whether I have stratified flow or droplet flow. So basically, what I am trying to tell you is, this is decided by the magnitude of the interfacial forces. If interfacial forces are high, you will have droplet flow. If the inertial forces are high, you will get stratified flow. Okay, we will see the details, but I just wanted to give you some background about what you are going to see and why it is important to do this. So if inertial forces are high, we get stratified flows. If interfacial forces are high, we get droplet flow. Now, these two sentences that I have written are high actually don't make any sense because I need to compare it with something else. Okay, that is the reason we talk in terms of dimensionless numbers like Reynolds number, Weber number. Okay, you're comparing two forces. Okay, so high with respect to what? That I have not told you yet. Okay, so whenever you have these dimensionless numbers, there's always a ratio of two forces. So if I say Reynolds number high, I mean inertial force is more than viscous force. If I say low, inertial force is less compared to viscous force. So similarly, when you talk about Weber number, capillary number, where I bring in the concept of surface tension. Okay, so high and low actually is a totally useless thing to say because I need to tell you high with respect to what, low with respect to what. Okay, so the ratio of forces is important. So this basically tells me, brings me to the concept of dimensionless numbers. Okay, so when you are solving problems, okay, in order to solve the full problem, like I explained earlier, it's very challenging, very difficult. So you will possibly be looking at some regime, low Reynolds number regime, low Weber number regime for doing the solution because the full problem is non-linear and getting a solution for the full problem, you may have to go to the computer and write some code, try to get an understanding. Okay, that is one way to do it. But when you write a code in a computer and get some results, number one, you have to check whether those results are right. So then you will go to some limit of low Reynolds number. Because that problem you can possibly solve analytically, okay, and get an understanding of in low Reynolds number how does the flow, how is the system behaving. Then you can validate your computer results at low Reynolds number with your analytical results. That will give you confidence in the results your computer program is giving. Then you use your computer program which you are confident about to go and do the simulation at higher Reynolds number, which you cannot do analytically. Okay, do you understand what I am saying? In some limiting cases, like low Reynolds number, you may be able to get solutions to the laminar flow profile, for example. Okay. Now you should run your code in the computer for the same conditions and see if the results generated by the computer code are matching with your analytical results which you got by deriving. If they match, then there is consistency between your analytical results and your computer code. If they don't match, that means either your analytical solution is wrong or your computer code is wrong or both are wrong. Okay, even if they match, they could both be wrong and still match. That's a different story. But what I'm saying is you need to start thinking about what exactly you're getting and to be able to interpret things. So once this match is happening and you have confidence that yes, it's working, then you say, look, I can simulate a higher Reynolds number flow by using my computer code because this is useless. My analytical code is valid only for low Reynolds number. Okay, so you need to do a high Reynolds number, I'll go to the code and do it. So you need both. So this business of doing things in the limit of low Reynolds numbers is what we call asymptotic analysis. We are looking at the asymptote of low Reynolds number or where I get analytical solution. That gives me understanding of the problem of the system. The computer code gives me understanding to a limited extent. Okay, so because you are putting in so many parameters and you see some effect, you do not know what is causing this physical effect. Okay, it could be because of velocity, it could be because of pressure, it could be because of surface roughness, it could be anything. So you're totally lost. Okay, because your code has all these factors inbuilt. So one has to, therefore, there is a need to do the analytical approach, this asymptotic analysis. There's also a need for computer code, but you need to understand the plus points of each method. okay, and then decide what is going to be your strategy for analyzing a problem, okay. I mean, it is not that one is superior, one is inferior. Both have advantages and disadvantages. You need to understand that advantages here, the disadvantages here, advantages there, disadvantages there, okay, and try to make the best by understanding both the approaches properly. As far as this course is concerned, we are going to focus very little on computer programming. Maybe some computer programming will be there, okay, some basic coding in MATLAB, which will be basically to graph and plot some of the results that you may generate so that you can understand things better, okay. Emphasis is not so much on MATLAB coding, but you may have to use it. So, if you are not familiar with MATLAB, I would suggest you do something and get comfortable with MATLAB, okay, but not very high intense MATLAB, I don't think. And so the point is, dimensionless numbers help in asymptotic analysis. For example, if Reynolds number is very much less than 1, that's what I mean, asymptote, very, very low Reynolds number, okay. We use this to validate computer code. The computer code can be for any Reynolds number, and once I validate, I say consistency between both the analytical method and the computer code, then I can use the computer code to analyze for high Reynolds number, okay, high Reynolds number with confidence, okay. Otherwise, you won't be confident if you don't do the validation step. So now, I just want to tell you that just one example I'll give and then we'll stop, because it is not just regular chemical engineering systems like evaporator, heat exchanger that we are talking about. There are today the chemical engineering profession is possibly one of the most versatile professions, and people are able to work across different areas. For example, just give one example. People use ultrasound for doing scan, okay, and body scan, all kinds of scans. And there, normally what happens is you are interested in understanding how does the sound wave propagate in the body for getting good results, because you are getting better contrast, okay. So there are lots of applications of this kind where people are actually, you need to understand in the presence of an ultrasound, okay, how does the flow behavior change. And there is a big impact in the field of medical diagnostics, okay. I am just giving you one example, there are many other examples possible, where a fundamental understanding of things like ultrasound flow in blood is extremely important, so that you can possibly come up with better treatment methods. And here the problem is complicated because you will possibly put a small gas bubble, okay, which is there in your blood flow. You pass ultrasound, this gas bubble is going to oscillate, okay, and because of that it is going to generate flow. This flow will have an effect on the shear stress at the walls of the blood vessels, and if there is a drug, because of the shear stresses which are acting on the walls of the blood vessels, the drug is able to penetrate, and you can possibly have improved treatment methods for cancer. So the point I am making here is if you understand the fundamentals properly, you don't have to restrict yourself to only chemical reaction engineering, distillation columns, extraction columns, heat exchangers. You will be able to extend the concepts to a wide variety of areas. Okay, could be medical diagnostics, could be anything else you want. So that's the whole idea. So the focus is on the fundamentals. You understand the fundamentals, then you will be able to apply it to any system. Okay, thank you.